Section 12.3, infinite sequences and series. Got one definition to start with, infinite sequence. It's just simply a sequence which has infinitely many terms. Now we could think that arithmetic and geometric sequences are also infinite sequences, but there's a whole array of sequences that are not arithmetic or geometric that are still sequences, and we're going to focus today on those types of sequences, the ones where we don't multiply by 2 every time or subtract 6 every time to get to the next term. It's going to be a little more complicated than that, a little more complex than just one simple operation to get to the next term. So let's consider this sequence 1, 1/2, 1/3, 1/4, 1/5. Just as a side note, this is called the harmonic series or harmonic sequence. I'm not going to require you to know that, but that is the name of this specific sequence: 1, 1/2, 1/3, 1/4, 1/5, and so on. That's the harmonic sequence. If we were adding them, it'd be the harmonic series, but that's kind of just a little side note. The formula for this sequence is the nth term is going to be equal to 1 over n, because if it's the first term, it's 1 over 1, second term would be 1 over 2, then 1 over 3 for the third, 1 over 4 for the fourth, 1 over 5 for the fifth, and so on down the line. So the formula for this sequence is a sub n, the nth term is equal to 1 over n. The question becomes, as n gets very large, what happens to each term? And what I hope you can see, we'd have 1/6, then 1/7, then 1/8, then 1/9, and eventually we'd have 1/100th, and then 1/500th, and then 1/1000th, and then 1/1,000,000th. Basically what happens here as n gets very large, what happens to each term is that it gets closer, whoops, let's spell closer, right? Closer and closer to 0, but the question is, will it ever get there? And the answer to that is no. As long as you have 1 in the numerator, you're never going to have 0. So we'll say it gets closer and closer to 0, but never actually gets there. Okay, and that brings up one of the biggest ideas in section 12.3, and that is the idea of limits. Okay, a limit is a number a function or sequence approaches as x or n approaches a number a. Now that number a is usually positive or negative infinity. So as x gets, like in the harmonic sequence here, as n gets very, very large, as n approaches infinity, what do we approach? Well, the answer there is 0. So the limit of this function is 0. Okay, so the notation for limits looks like this. We have the limit as n goes to infinity of 1 over n is equal to 0. And as you can see, I just read that out right here. So the limit as n goes to infinity of 1 over n is 0. And that's kind of what this sentence is right here. That's kind of how you say that out loud. When you see notation like this, the limit as n goes to infinity of whatever your sequence or series or function, whatever it might be, is 0. Okay, so as n gets very, very large in this sequence, 1 over n, we're going to be approaching 0. We're never going to get there, but the limit, as we get bigger and bigger and bigger with our n's, we're going to get closer and closer to 0. Okay, so estimate the limit. So we're given a sequence, 1/2, 7/9, 17, 28, more and more and more, and then it's kind enough to give us the actual formula for the sequence. So the first term, 2 times 1 squared minus 1 is 1. 1 cubed plus 1 is 2, and so on down the line. So this is the formula we're going to use. Now to actually estimate the limit, what we're going to do is we're basically going to find, the bigger and bigger terms. So what I would do first, let's find the 50th term. And how we would do that is we simply plug and chug into this formula. So we're going to take 2 times 50 squared minus 1 all over 50 cubed plus 1. And what we're going to find out is that this is approximately 0.04. And again, this is going to be rounded answers because we are asked to estimate. We don't need to be terribly precise, but we just want to kind of see what happens as n gets very, very large. So we do the 50th term, then let's take a look at the 100th term. And again, it's just plug and chug, 2 times 100 squared minus 1 all over 100 cubed plus 1. If you're going to type this in your calculator, which I would definitely recommend, make sure your numerator is in parentheses and your denominator is also in parentheses. Otherwise, the calculator is not going to do it correctly. When you type in the 100th term, what you're going to get is approximately 0.02. Then after we find the 100th term, we can maybe see that it's probably going to 0, but we should probably just double check that or keep going with our terms so we can make a better educated statement. So after we find the 100th term, let's find the 500th term. The 500th term. So we're going to take 2 times 500 squared minus 1 all over 500 cubed plus 1. And when you type that in your calculator, you're going to get something like 0.004. So we're adding another 0 before our numbers. That's probably a good thing that when we said we're probably headed to 0, this is kind of confirming that. And just to be double sure, let's find the 1,000th term. Okay, if you want to find the 10,000th term or the 100,000th term or the 250,000th term, it's up to you. But that should be enough. If you can find 4 terms as you get progressively larger, you should be in good shape. So 2 times 1,000 squared minus 1 all over 1,000 cubed plus 1. And again, rounded in the calculator, this is going to be 0.002. So we can make our limit statement. We'll say that the limit as n approaches infinity of our function or our sequence, which was 2n squared, not minus 1 or plus 1, minus 1 over n cubed plus 1 is 0. Because as we get progressively larger, we're getting closer and closer to 0. Let's try another one here. 9/5, 16/14, 65 over 27, blah, 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 more terms. Eventually we come to find 7n squared plus 2 over 2n squared plus 3n. Again, let's find the 50th, the 100th, the 500th, and the 1,000th term. I'm not going to show you the plug and chug part. I'm just going to kind of list these out here. So the 50th term is going to be equal to about 3.398. Again, this is just calculator work. The 100th term is somewhere in the neighborhood of 3.448. The 500th term, again, plugging and chugging, 3.4895. The 1,000th term is roughly 3.495. So as we get progressively larger, what I hope you see is that we're getting closer and closer and closer to 3.5, but I bet you if you typed in the 10,000th term or the 100,000th term or the millionth term, what you're going to find is you're still not going to quite get to 3.5. So what I think we can say for our limit here, if we're estimating this limit, the limit as n goes to infinity of 7n squared plus 2 over 2n squared plus 3n is going to be equal to 3.5. There are ways to find limits, not necessarily where we plug and chug into a calculator. There are theorems that allow us to find limits algebraically or intuitively. So I want to talk about those here real briefly. So with these limit theorems, we have to assume a sub n and b sub n are sequences, and their limits as n goes to infinity, not exits, exists. Let me rewrite that. That might have been an autocorrect thing. Exists. And that c is a constant. Okay, so that's just kind of bear with me here. So the limit of a sum. So the first theorem says that if I have the limit as n goes to infinity of the sum of two different sequences, a sub n plus b sub n. What this theorem says is that we can split this up into the sum of two separate limits. So we can take the limit as n goes to infinity of the first sequence plus the limit as n goes to infinity of the second sequence. Okay, so remember, these are sequences up here. So let's say this is a sequence, and if we go back, this is also a sequence. If we were going to add these two sequences together and find the limit, what we can do is we can find the individual limits of each one like we did earlier and then add the two limits together. So if we were to add, the first two examples from our notes, the limit as we combine them would be 3.5, because we would take 3.5 plus 0, and so our limit as we add them together would be 3.5. Okay, if we were subtracting them, the limit of a difference, so if we have the limit as n goes to infinity of a sub n minus b sub n, very similar to sum, we can split this into the difference of the two limits. So the limit as n goes to infinity of a sub n minus the limit as n goes to infinity of b sub n. Okay, so just like if we were adding the two sequences, if we're subtracting them, we can subtract the two limits. Product and quotient works exactly the same way. We can say the limit as n goes to infinity of a sub n times b sub n. We can split this into the product of each individual limit. The limit as n goes to infinity of a sub n times the limit as n goes to infinity of b sub n. And with quotient, like I said, same thing. We can take, if we have the limit as n goes to infinity of a sub n divided by b sub n, we can split this into the quotient of each one. We can take the limit as n goes to infinity of a sub n and divide that by the limit as n goes to infinity of b sub n. Okay, so there's your four basic limit theorems. It'll basically, it's what it's going to do is it's going to allow us to work things out more in our favor, so we can find better limits. Now the last one here, the limit of a constant, what this one says, because remember up here I said c is a constant, so if you're taking the limit as n goes to infinity of, let's say c of n is equal to c, so every term in my sequence is the same number. So like my sequence would have to be like 3, 3, 3, 3, 3, and forever, okay? So if we're taking the limit of a constant, okay, the limit of a constant is that number, okay? It's really hard to write this out. The limit as n goes to infinity of a series of constants is that constant. So we could say the limit of c of n, where c is a constant, is c. So I guess technically it should be this. So here's our limit, just like it was up here. This is equal to c, where c of n is equal to c for each n. For each n. So if our c of n was just a bunch of 3's, then the limit would be 3. That's kind of what it's saying. It's kind of a duh type of thing, but it's kind of nice to have that in our back pocket to use. Okay, so let's actually use some of these theorems to find limits. Now, the limit as n goes to infinity of 1 plus 3n squared over n squared. In order for us to be able to use those theorems that we just talked about, something that was kind of overlooked maybe a little bit, the key word here, the limit has to exist, meaning it has to approach some number as n gets very, very big. Just like this one got really close to 3.5, this one got really close to 0. With this one, you know, if we think about 1 plus 3n squared, that would be our first sequence. So we could you could use the quotient theorem to say the limit as n goes to infinity of 1 plus 3n squared divided by the limit as n goes to infinity of n squared. The problem with this is both of these limits, neither of these limits exist, because as n gets really big, this gets really, really big. This doesn't approach a number. This just goes up and up and up and up and up and gets bigger and bigger forever. Same with this one. Okay, so we can't use the quotient property to do this. How we're going to do this, how we're going to get around that, and if you want to mark this off to the side, is what we're going to do is we're going to use the Hart method. We're going to rewrite the expression using the Hart method, M-E-T-H-O-D method. Okay, we're going to rewrite the expression using the Hart method. And if you remember the Hart method, we're going to take everything on the top and divide it by what's on the bottom. So this is going to become the limit as n goes to infinity of 1 over n squared plus 3n squared over n squared. Now, this 1 over n squared, as n gets really, really big, that's going to get really, really close to 0. So that does exist. And I'm going to actually kind of simplify this out just a little bit more. I'm going to say the limit as n goes to infinity of 1 over n squared. There's really nothing we can do there. Plus, now 3n squared over n squared. They both have n squared on the top and the bottom. So what we can really do is we can kind of just cross them out, and that leaves us with 3. So limit as n goes to infinity of 1 over n squared plus 3. Now we can use our theorems because now the limits of both of these both exist. Okay, so we can make this equals the limit as n goes to infinity of 1 over n squared plus the limit as n goes to infinity of 3. these are pretty straightforward to figure out. So as n gets really, really big, as I get 1 over something incredibly large, 1 over something incredibly large is essentially 0. And this one is that last theorem I was just talking about, the limit as n goes to infinity of a constant. Well, as each number is 3, as I get really, really big with my n's, it's still going to be 3. So this is going to be 0 plus 3, which is equal to 3. So the limit as n goes to infinity of 1 plus 3n squared over n squared, as n gets really big, we're going to get really, really close to 3. And that's your answer right there. Let's try another one here. Number 2. We're going to have the limit as n goes to infinity of 3n plus 6 over n. Once again, we can't use our theorems right away because as this gets really, really big, I'm not approaching anything. Same with this one, I'm just going up forever. So what I need to do, again, I'm going to use the Hart method to split this up, just like that. Okay, so we can rewrite this. I just want to keep my colors, so I went with purple first. So we're going to have the limit as n goes to infinity of 3n over n plus 6 over n. Once again, I'm going to simplify some things. I can take out those n's right there. So this really becomes the limit as n goes to infinity of, let's see, that's 3 plus 6 over n. Now I can use my my theorem, my sum of a limit theorem, to make this the limit as n goes to infinity of 3 plus the limit as n goes to infinity of 6 over n. And we'll just kind of use our intuition again. The limit as n goes to infinity of 3, well, that's just 3 again. It's a constant. The limit as n goes to infinity of 6 over n. So this time we have 6. The last time we had 1. But as long as this is just a massive number, I'm not saying like, 25. I'm thinking like 250 million. 6 over 250 million compared to 1 over 250 million, essentially it's the same thing. As n gets really, really big, eventually this thing's headed to 0. Remember, we're talking really, really big numbers here, something that we can't even fathom in terms of a value. So if we get 6 over something astronomically large, that's basically 0. It's approaching 0. It's never going to get there, but it's going to get really, really close to 0. So again, 3 plus 0, that's 3. So finally, to make this a final answer, what we can say then as the limit as n goes to infinity of our original expression, 3n plus 6 over n, that would be equal to 3. And that is your final answer. The next couple of examples here are a couple of examples where the Hart method isn't going to work, specifically because maybe we don't have something that allows us to use the Hart method, like a binomial. We need one term here to be able to do this, and that's not going to work. So if this happens again, once again, we can't use our quotient property or our quotient theorem because both of these limits go to infinity. Technically they don't exist. That's what that means. So what we need to do is, if we get caught with something like this, and I would definitely jot this down off to the side, if the Hart method is not an option, so if the Hart can't be used, what you're going to do is you're going to divide each term in both the numerator and the denominator, so each or every term, whatever, by the highest power in the denominator. Highest power, I should say highest power of n. So let me get rid of that. Highest power of n in the denominator, or whatever variable, denominator, whatever variable you might be using in the specific exercise. So in this case it's n. The highest power is n squared. So what we're going to do is we're going to divide each and every one of these terms by n squared. So all 5 of them. So we're going to make this look like this. It's going to be the limit as n goes to infinity of 5n squared over n squared plus n over n squared minus 4 over n squared. All that gets divided by n squared over n squared plus 1 over n squared. Okay? Now, this needs to be cleaned up severely. Okay? We have lots of n squareds. We have lots of n's. Let's see if we can't simplify some things. N squared and n squared in the first term, that goes away. N squared and n, that goes away, that goes away. 4 over n squared, that's nothing we can do. N squared over n squared, that's 1. And then 1 over n squared, we can't do anything with that. So really this is equal to the limit as n goes to infinity of, let's see, we're left with 5 plus, we're going to have 1 over n minus 4 over n squared, all over 1 plus 1 over n squared. In the interest of saving time, what I'm going to do is I'm going to use 3 theorems. I'm going to use the sum, the difference, technically 4. Sum, difference, quotient, and then constant twice. But just like in the previous 2 examples, once we have it split apart, we're just basically evaluating each limit individually. I'm going to do the same thing here, but I'm going to keep everything kind of closely knit together. Okay, so what it's going to look like is this. So as we basically get really large, as 5 gets really, really large, this is going to stay at 5. As n gets really, really large, 1 over n, 1 over a really big number, essentially is 0. Okay? 4 over n squared, same thing happens. As n gets really big, 4 over something astronomically large is still going to look an awful lot like 0. So that's going to head towards 0 as n gets really big. 1, as n gets really big, is going to stay 1. And then 1 over n squared, as n squared gets big, just like this one. Whether it's 4 on top or 1 on top, even if it was 4,000 or 1 million, as this gets super large, it's really not going to matter. This is still going to approach 0. So really, I'm just kind of evaluating each limit individually and then just kind of using my theorems kind of as I go. So really what this leaves me with, the numerator, 5 plus 0 minus 0 is 5. And then 1 plus 0 on the bottom is just 1. So 5 over 1. What we can say then is the limit as n goes to infinity of our giant mess, which was 5n squared plus n minus 4 all over, what do we have, n squared plus 1, this is equal to 5. Kind of an anticlimactic, oh, it's just 5 for something that looks really big and ugly. In the last example here, you're going to actually have an option to either use the Hart method or dividing by the highest power. Either one's going to work here. So number 4, we're going to have the limit as n goes to infinity of 2 plus 5n plus 4n squared all over 2n. Now, like I said, you can use the Hart method or you can divide by the highest power. Either one's going to be fine. I'm going to use the Hart method, but in this example, the doing either one's going to give you the exact same thing. So it's really not going to matter in this case. So the limit as n goes to infinity, 2 divided by 2n, I'm just going to simplify it right away. Again, I'm trying to save a little bit of time here, so that's 1 over n. 5n divided by 2n, well, the n's are going to cancel, so that leaves me with 5 halves. And 4n squared divided by 2n, the 4 and the 2 simplify to 2, n squared over n is n. So this simplifies down into 1 over n plus 5 halves plus 2n. Now, again, we're going to use the sum of a limit theorem. So we're going to split this up into 3 separate parts. I'm going to split this one up actually here. So this is going to be the limit as n goes to infinity of 1 over n plus the limit as n goes to infinity of 5 halves plus the limit as n goes to infinity of 2n. Now, as n gets really large in the first one, 1 over something really, really big, we've seen that several times already today, that's 0. The limit as n goes to infinity of 5 halves, again, this is a constant, so that's going to remain 5 halves, and that's plus. Now the real question here, the limit as n goes to infinity of 2n. As n gets really, really big, we're just multiplying it by 2. It's going to continue to get really, really large. So this is going to be infinity. And if you ever get something like this, where something goes towards infinity as n gets really, really big, that's okay. What this means is that the limit does not exist. So you have two ways you can write this. You can say the limit, let's try writing that properly, the limit dne does not exist, or what you can say is there is no limit. Either one is fine, okay? So there are going to be times where your limit doesn't exist, or you're going to be going towards infinity. If it ever goes towards infinity, then you do not exist. The limit does not exist, and that's okay. That's an option in different examples, okay? So don't think that you're always going to get a number, because sometimes you won't, and that's okay.